Okay, so we're picking up here. And ionization energy and atomic radius have what kind of relationship? Direct or inverse? Inverse. Every time that we see a trough, a dip in ionization energy, we have a larger atomic radius. Okay? Every time we see a spike in ionization energy, we have the lowest atomic radius for that period. And it just makes sense. The things that are holding their electrons more closely are harder to get electrons from. The things that have their electrons held far out from the nucleus, that are heavily shielded, those are really easy to get electrons from. They tend to not hold their electrons as tightly. So far we've talked all about ionization energy, and that's the process of doing what? Making an ion by taking away an electron. So ionization energy, and this is important, IE is all about removing electrons. So when we're talking about ionization energy, we are only talking about creating then what kind of ions? Positive or negative? We remove an electron, what kind of ion do we get? Positive. And I had some freshmen in last night for physical science for tutoring. And the thing that when I taught physical science, I used to always do this, and I think you guys get this intuitively at this point, but for some people, nobody's ever laid it out this clearly or this simply. If I have 3 protons and 3 electrons, I can be neutral because they each cancel one another out. If I take away one of those electrons, now those cancel one another out, and I have a 1+ charge. And with freshmen who really had no concept of atomic charge and ions, I used to actually make them draw little plus and minus signs because they could not figure out. It wasn't automatic that, oh, you take away 2 electrons, you now have a +2 charge. Oh, you add an electron. So what happens if we add an electron? Whoops. If we add an electron, now all these cancel one another out. I have a 1- charge. And I think, like I said, you guys get that. That's not hard, but for freshmen in physical science, that's always sort of a conceptual leap that they haven't made yet. So ionization energy is all talk about making positive electrons because or positive ions because we're removing electrons. Are all ions positive? No. We have lots of negative ions. So that gets us to our next idea. Okay, so now we talk about electron affinity. And a lot of you already got to the homework questions on this. If we add an electron to a neutral atom, so for instance, fluorine loves to take on electrons. Fluorine is like the crazy cat lady of electrons. Oh, look, there's a cat. I mean, an electron. Sure, it can come home with me. Fluorine, chlorine, bromine, iodine all want to take electrons. Actually, they're not the crazy cat ladies because they stop at 1 electron. But they really want that 1 electron. The way this is worded is tough at this level. Notice that it says the energy change for this is electron affinity. We're not saying that it's the amount of energy it takes to add an electron. We're talking about the change in sort of potential energy for the atom. So to talk about this, the best metaphor really is gravitational potential energy because they're similar in some ways. And when we talk about energy changes in chemistry, it's a useful metaphor. So if we have, let me change that color. If we have a rock at the top of a hill, is it stable? Not really. It's got a lot of potential energy. Having a lot of potential energy really, in effect, means that you are unstable. Because you've got the potential to spend that energy. It can convert that to kinetic at any second. You go rolling down that hill. When we have an atom like fluorine, that is one electron away from looking like a noble gas. It's like a rock sitting at the top of a hill. It's not really stable. Once it gets, so if this is fluorine, if that rock rolls downhill and becomes a fluorine ion, it is more stable, okay? The fluoride ion, the F minus 1 minus, is more stable than a neutral atom of fluorine. If we think about this hill as an amount of energy, the difference between this amount of energy and this amount of energy, that difference, and I'm going to have to shrink this so I can write a little bit more. That difference in energy is the energy change that we're talking about. Okay? The amount of difference in energy between that neutral atom and that atom that has gained an electron. So this next concept, and the other sort of metaphor or analogy that works well here. Remember me talking about the strawberry fields? Did we talk about putting water on strawberries at night before a frost?
Yeah.
Okay. The water gives up its heat when it drops to a lower energy state. It goes from being a liquid to a solid. It gives up energy. Energy is released out into the environment. When this fluorine goes from being at this high energy, unstable state, and it drops down to this lower energy state, that difference in energy goes where? Just like the water on the strawberries. It goes out into the environment. It's released. So if energy is released when an atom accepts an electron, meaning that it's more stable because the atom with that electron is now lower energy and hence more stable, then we consider the electron affinity for that atom to be a negative number. Conceptually, that doesn't make sense unless you think about it in terms of this metaphor. You can think about it in terms, it makes great sense if you're in physics, because it's like change in position. Sure, it's lower, so it's a negative number. Ignore that, sorry. This is a negative number because the energy state is lower than it was to begin with. That's about the best we can do explaining it in a high school Chem 1 class. If you go on to take more than just a year of general chem, if you do any sort of, like the thermodynamics of reactions and things like that, you'll go into a lot more depth with this idea. We don't go into a lot more depth here because that's enough. That's plenty. Okay, now, here's the opposite case. You know, so let's shrink this down. What does sodium want to do in terms of electrons? Get one, give one up. And again, remember, we're using want as a metaphor. Atoms don't actually want anything. Does sodium by nature give up electrons or take them on? Gives them up. Sodium would love to lose an electron and be a positive atom. So if we have sodium sitting here, okay, and let's say that's actually we could make this a really extended metaphor. Sure, why not? Let's say that this is a sodium ion. So this is sodium that's already lost an electron, and it's got a +1 charge. That sodium 1+ ion is more stable, lower energy, than the sodium that had all of its electrons, the neutral sodium. Yes? So it's lower energy, it's downhill from the neutral sodium. What if we somehow forced sodium to take an electron? So we took that sodium boulder. Let me move this whole thing over just a little bit. And we actually forced sodium to take an electron, and we made it a sodium 1-. It's got an extra electron. So we've pushed it up that hill. It's even higher energy and less stable than it was when it was a neutral atom. So this is, why can I never spell neutral? It's got even more energy because it's completely unstable. This is, frankly, this is like handing me a raisin cookie. If I don't have to touch the raisin cookie, I'm not going to. Like, if you put it in my hand, I'm pretty much going to do that, like it's something that's on fire, because I think raisins are disgusting. You can't make me take a raisin cookie. And you can make me take it, but I'm going to sit it down the minute your back's turned. Or I'm just going to drop it and let the dog eat it. It's gross. Ugh. And if some of you love raisin cookies, good for you. You can have mine. I'll take your chocolate chips. So, oops, if I do that, I'm in front of the board. We would consider this change in energy to be a positive electron affinity. This would be a positive EA. It's totally unstable. It's not going to stay there. The second you let go, this is like holding an electron down onto a surface. The minute you let go, it's going to pop right back off. You can't make it take an electron because it doesn't want one. So that would be a positive electron affinity. Well, positive electron affinity ions, they're not stable. They're not going to keep that electron. They're going to dump it the second they can. So we go from positive EAs in the group 1 and 2s to very, very, very strongly negative EAs over in group 17. And of course, the noble gases are totally stable as is. I don't even think they're classified as having electron affinities. I'd have to check that. But because there's not an energy change because they don't take or give electrons. Okay, let's talk about ions really quickly. In physical science, I think that you use the terms cation and anion a lot. Who's got a handy mnemonic for remembering which is which? Anybody got a handy memory device for remembering cation versus anion? Really? Oh, okay. I always do. I love cats. I love cats. I feel very positively about cats. Point of truth, I'm not a cat person. I'm more of a dog person, but it doesn't matter. Positive feelings about cats. Positive feelings about cats. You can draw a terrible cat. You can not draw a cat at all. Positive ions are cat ions. You hope that was going somewhere. Positive ions are cat ions. Anybody here anti-anything? I'm anti-raisins. Strongly anti-raisins. Ugh. You got strong feelings about something. Could be anything. I think some of you have strong feelings about certain things. Okay, that's not going to work well for you on this. So you'll have to do some sort of trick yourself mnemonic. So if you have, like, I am anti-raisin. I have strong negative feelings. If I could prohibit raisins on the planet, I would. I think they're just morally offensive on every level. Little mummified grapes. Sorry if I'm offending any of you pro-raisin people. If you are anti-something, you're against it, you have negative feelings about it. A negative ion is an anion. Just like being anti-something. Okay? So, we've established that. Now, here's the good part. When we make a positive ion, the radius shrinks a little bit. Whoa. That's weird. So I'm gonna construct one of my concentric ring atom thingies. We're gonna pick up with cation and anion formation and its effect on atomic radius tomorrow. So homework will not be due until Thursday, and that's what we got. Happy travels, folks.